Welcome to Building Scalable Distributed Systems, Week 5. In this section, we're going to focus on the pertinent issues in achieving scalability for the services tier in an application. We'll explore API and service design and describe the salient features of application servers that provide the execution environment for our services. We'll also elaborate on topics such as horizontal scaling, load balancing, and state management that we introduced in the previous sections. So in this module, we'll talk about HTTP API design, servlets, application service containers and how they operate to host our services, and horizontal scaling and load balancing. And in the next section, we'll talk about caching both at the application level and within the internet. In the simplest case, an application comprises one internet-facing service that persists data to a local data store, as shown on the slide here. Clients interact with the service through its published API, which is accessible across the internet. Let's look at the API and service implementation in more detail. An API defines a contract between the client and the server. The API specifies the types of requests that are possible, the data that is needed to accompany the requests, and the results that will be obtained. APIs have many different flavors, as we explored in the RPC and RMI discussions in Week 4. While there remains some API diversity in modern applications, the predominant style relies on HTTP APIs. These are typically, although not particularly accurately, classified as RESTful. REST is actually an architectural style that was defined by Royal Fielding in his PhD thesis. A great source of knowledge on RESTful APIs and the various degrees to which web technologies can be exploited in REST is REST in Practice by Weber & Co. Here we'll just briefly touch on the HTTP CRUD API pattern. This pattern does not fully implement the principles of REST, but is widely adopted in enterprise systems today. CRUD stands for Create, Read, Update, Delete. A CRUD API specifies how clients perform these operations in a specific business context. For example, a user might want to create a profile, read a catalog item, update their shopping cart, and delete items from their order. A HTTP CRUD API makes these operations possible using 4 core HTTP verbs, as shown on the slide here, namely post to create a new resource, get to read a resource, put to update a resource, and delete to delete a resource. A HTTP CRUD API applies HTTP verbs on the resources identified by a Uniform Resource Identifier, or a URI. So from the previous slide, we could apply an operation to this URI, which identifies a specific skier, 768934. A HTTP GET request to this resource would return the complete profile for the skier in the response payload, such as their name, address, number of days visited, and so on. If the client subsequently sends a HTTP PUT to this URI, we are expressing the intent to update the resource for this skier. In this example, it would be updating the skier's profile. The PUT request would provide the complete representation for the skier's profile as returned by the GET request. Again, this would just be as a payload with the request. Payloads are typically formatted as JSON or XML or text, and other formats are actually possible. If a client sends a delete request to the same URI, then the skier's profile will be deleted. Maybe they didn't pay for their passes. HTTP APIs can be specified using a specification notation called OpenAPI. At the time of writing, the latest version is 3.0. A tool called SwaggerHub is the de facto standard to specify APIs in OpenAPI. The specification is defined in YAML, and an example is shown on the slide here. It defines a GET operation, and the URI is resorts. If the operation is successful, a 200 response code is sent, along with a list of resource a list which represents the resorts in a format defined by a JSON schema. If the request is unsuccessful, then we can return either a 400 if, for example, the database query failed, or the input was invalid, or if the server fails, we would get a 500 response. The application server container receives requests and routes them to the appropriate handler function to process the request. The handler is defined by the application and implements the business logic required to generate results from the request. As multiple simultaneous requests arrive at the service instance, each is typically allocated a thread to execute the request. The sophistication of the routing functionality varies widely by technology platform and programming language. For example, in Express.js, the container calls a specified function for requests that match an API signature, known as the route path and HTTP method. And you can see an example of this on the slide. We have a method that will be called when the client gets a GET request for a specific skier profile as identified by the value skier ID. In Java, the Spring framework provides an equally sophisticated method of routing. It leverages a set of annotations that define dependencies and implement dependency injection to simplify our service code. Again, we have an example on the slide of these annotations. We have one which defines a REST controller, identifying the class as a controller that implements an API and automatically serializes the return objects into a HTTP response returned from the API. We also define the mapping to the API with the getMapping annotation. This maps the API signature to a specific method and defines the format of the response body, i.e. JSON. We also have a path variable annotation, which identifies the parameter as the value that originates in the path from the URI that maps to this method. The Java Enterprise Edition defines servlets, which also provide annotations, as shown on the slide here. The web servlet annotation identifies the base pattern for the URI, which should cause a particular servlet to be invoked. This would be /skiers in our example. The class that implements the API method must extend the HTTP servlet abstract class from the javax.servlet.http package and override at least one method that implements a HTTP request. The HTTP verbs map to the methods as follows, shown on the slide. A GET request goes to the doGet method, a POST goes to the doPost, a PUT to the doPut, and a DELETE to the doDelete. When we define one of our servlet methods, each is passed as a parameter a HTTP servlet request and HTTP servlet response objects, as we see here. The servlet container creates the HTTP servlet request object, which contains members that represent the components of the incoming HTTP request from a client. This object contains the complete URI path for the call, and it's the servlet's responsibility to explicitly parse and validate this and extract path and query parameters if they are valid. Likewise, the server must explicitly set the properties of the response using the HTTP servlet object. Here you can see it's setting response properties. Servlets therefore require more code from the application service programmer to implement. However, they're likely to provide a more efficient implementation as there's less plumbing involved when compared to the more powerful annotation techniques of Spring and other technologies. A good rule of thumb is that if a facility is easier to use, such as a programming framework, it's likely to be less efficient. This is a classic performance versus ease of use trade-off, and we'll see lots of these in this class. State management in application services is a tricky, nuanced topic. The bottom line is that service implementations that need to scale should avoid storing conversational state. What on earth does that mean? Well, let's start by examining the topic of state management with HTTP. HTTP is known as a stateless protocol. This means each request is executed independently without any knowledge of the requests that were executed before it from the same client. Statelessness implies that every request needs to be self-contained, with sufficient information provided by the client for the web server to satisfy the request regardless of any previous activity from that client. However, the picture's a little bit more complicated than this simple description portrays. For example, the underlying socket connection between a client and server is kept open so that the overheads of connection creation are amortized across multiple requests from a client. This is the default behavior for versions HTTP 1 and above. HTTP supports cookies, which are known as the HTTP state management mechanism. Kinda gives it away, really. HTTP 2 supports streams, compression, and encryption, all of which require state management. So originally HTTP was stateless, but perhaps not anymore. Armed with this confusion, let's look at the application services APIs that we can build on top of HTTP. When a user or application connects to a service, it will typically send a series of requests to retrieve and update information. Conversational state represents any information that is retained between requests, such that the subsequent request can assume the service has retained state about the interactions. Let's look at an example. In our Skier API, a user may request their profile by submitting a GET request to the following URI as shown on the slide here. They may then use their app or web browser to modify their phone number and send a PUT request to the URI designed for updating this field. So here we send a PUT to the API specifying a phone number and the new phone number for the skier. Note this URI does not identify the skier. Hence the service must know the unique identifier of the skier, namely 768934. Hence for this PUT operation to succeed, the service must have retained conversational state from the previous GET request. Implementing this approach is relatively straightforward. When the service receives the initial GET request, it creates a session state object that uniquely identifies the client connection. In reality, this is often performed when a user logs into a service. The service can then read the skier profile from the database and utilize the session state object to store conversational state. In our example, this would be the skier ID. When the following PUT request arrives from the client, it uses the session state object to look up the skier ID associated with this session and uses that to update the skier's phone number. Services that maintain conversational state are known as stateful services. Stateful services are attractive from a design perspective as they can minimize the number of times a service retrieves data, i.e. state, from the database and reduce the amount of data that is passed between clients and services. For services with light request loads, they can make eminent sense and are actually promoted by many frameworks to make services easy to build and deploy. For example, Servlets supports session management using the HTTP session object, and similar capabilities are offered by the session objects in ASP.NET. As we scale our service implementations, however, the stateful approach becomes somewhat problematic. For a single application server, we have two problems to consider. Number one, if we have multiple client sessions all maintaining session state, this will utilize available server memory on the node that our service is running. The amount of memory utilized will be proportional to the number of clients we are maintaining state for. If a sudden spike of requests arrives, how can we be certain we will not exhaust available memory and cause the server to fail? Secondly, we must also be mindful about how long to keep session state available. A client may stop sending requests but not cleanly close their connection to allow the state to be reclaimed. Like me, they might just wander off for a coffee and forget to log out or return to the session. All session management approaches support a default session timeout. If we set this to a short time interval, clients may see their state disappear unexpectedly. If we set the session timeout period to be too long, we may degrade server performance as it runs low on resources. In contrast, stateless services do not assume that any conversational state from previous calls has been preserved. The server should not maintain any knowledge from earlier requests, so that each request can be processed individually. This requires clients to provide all the necessary information for the service to process the request and provide a response. If we look back at our previous example, we could transform the put request to be stateless by incorporating the SKIA ID, namely 768934, into the phone number update. In reality, this is a pretty dumb API design. The API should in fact transfer the complete resource, the SKIA profile, with the GET response and the put request to update it. This means the GET request for the SKIA should retrieve and return the complete SKIA profile so that the client's application can display and modify any data items in the profile as the user wishes. The complete updated profile is then sent as the payload in the following put operation and used by the service to update the resource that is persisted in a database. You can see this on the slide here in the interaction diagram. Any scalable service will need stateless APIs. If a service needs to retain state pertaining to a client session, the classic shopping cart example, it must be stored externally to the service. This invariably means an external data store, or as we'll see later, a cache. We'll revisit this topic later in this session during the discussion of horizontal scaling. That's when stateless services really come to the fore. Application servers are the heart of a scalable application, hosting the business services that comprise our systems. Their basic role is to accept requests from clients, apply application logic to the requests, and reply to the client with the request results. Clients may be external or internal, as in other services that require to use the functionality of a particular service within the application. The technological landscape of application servers is broad and complex, depending on the language you want to use and the specific capabilities that each offers. In Java, the Java Enterprise Edition defines a comprehensive, feature-rich standards-based platform for application servers. This has multiple vendor implementations and open source alternatives. In other languages, the Express.js server supports Node, Flask supports Python, and in Golang, a server can be created by incorporating the net/HTTP package. These implementations are much more minimal and lightweight than the JEE alternatives and are typically classified as web application frameworks. In Java, the Apache Tomcat server is a somewhat equivalent technology. Tomcat is an open source implementation of a subset of the JEE platform, mainly the Java Servlet, Java Server Pages, Java Expression Language, and Java WebSockets technologies. This slide gives a simplified representation of the anatomy of an application server such as Tomcat. Tomcat implements a servlet container, which is an execution environment for application-defined servlets. Application-defined servlets are loaded into this container, which provides lifecycle management and a multi-threaded runtime environment. Requests arrive at the IP address of the server, which is listening for traffic on specific ports. For example, by default, Tomcat listens on port 8080 for HTTP requests and port 8443 for HTTPS requests. Incoming requests are processed by one or more listener threads. These create a TCP IP socket connection between the client and the server. If the network requests arrive at a frequency that cannot be processed by the TCP listener, pending requests are queued up in the socket's backlog queue. The size of the backlog is operating system dependent, but in most Linux versions it's around 100. Once a connection is established, the TCP requests are marshaled by, in the example on the slide, a HTTP connector. This generates the HTTP request that the application can process. The HTTP request is then dispatched to an application thread to process. Application container threads are managed in a thread pool, essentially a Java executor, which by default in Tomcat is a minimum of 25 threads and a maximum of 200. If there are no available threads to handle a request, the container maintains them in a queue of runnable tasks and dispatches these as soon as the thread becomes available. This queue by default is of size integer.max_value, that is essentially unbounded. If a thread remains idle for a default 60 seconds, it's killed by the Tomcat server thread pool to free up resources in the JVM. For each request, an instance of the servlet is instantiated. The servlet method processes the HTTP request headers, executes the business logic, and constructs a response that is marshaled by the container back to a TCP packet and sent over the network to the clients. In processing the business logic, servlets often need to query an external database. This requires each thread executing the servlet to obtain a database connection and execute database queries. As database connections are limited resources and consume resources in both the client and the database server, a fixed size connection pool is typically utilized. The pool hands out open connections to a requesting thread on demand. When a servlet wishes to submit a query to the database, it therefore requests an open connection from the pool. If one is available, access to the connection is granted to the servlet until it has completed its work. It then closes the connection. At that stage, the connection is returned to the pool and made available for another servlet to utilize. As the thread pool is typically larger than the connection pool, a servlet may request a connection when none are available. The connection pool maintains a request queue in these circumstances and hands out open connections on a FIFO basis, and threads in the queue are blocked until there's availability. An application server framework such as Tomcat is hence highly configurable to handle different workloads. The complete Tomcat container environment runs within a single JVM, and hence processing capacity is limited by the number of virtual CPUs available and the amount of memory allocated as heap size. Each allocated thread consumes memory, and the various queues in the request processing pipeline consume resources while requests are waiting. This means that the request latency will be governed by both the request processing time in the servlet business logic and the time spent waiting in queues for threads and connections to become available. In a heavily loaded server with many threads, context switching may start to degrade performance, and available memory may become limited. If performance degrades, queues grow as requests wait for resources. This consumes more memory. If more requests are received than can be queued up and processed by the server, then new TCP IP connections will be refused and clients will see errors. Eventually, an overloaded server will run out of resources and start throwing exceptions and crash. This is what you get when you mess with me. And server crashes are the catastrophes we really want to avoid. Time spent tuning configuration parameters on our application servers to efficiently handle anticipated loads is therefore rarely wasted. A rule of thumb is if CPU utilization consistently exceeds the 70 to 80% range, this is a signal of overload. Similar insights exist for memory usage. Basically, once any resource gets close to full utilization, systems tend to exhibit less predictable performance, as more time is spent, for example, thread context switching and garbage collecting. This invariably affects latencies and throughputs. Monitoring tools available with web application frameworks enable engineers to gather a range of important metrics, including latencies, active requests, queue sizes, and so on. These are invaluable to carrying out data-driven experiments that lead to performance optimization for your applications. Java-based application frameworks such as Tomcat will invariably support the JMX, the Java Management Extensions Framework, which is a standard part of the Java Standard Edition platform. JMX enables frameworks to expose monitoring information based on the capabilities of mbeans or managed beans. These represent a resource of interest such as a thread or a database connection pool. mbeans enable an ecosystem of tools to offer capabilities for monitoring JMX supported platforms. These range from JConsole, which is available in the JDK by default, to powerful open source technologies such as Java Melody and many expensive commercial offerings. And here you can see a screenshot from JConsole where it has the graphs showing the memory usage, the number of classes loaded, the threads that are active, and the CPU utilization. There's also other information available under these tabs. Getting to know your performance monitoring tool is a very, very good thing to do. A core principle of scaling a system is being able to easily add new processing capacity to handle increased load. For most systems, a simple and effective approach is deploying multiple instances of stateless server resources and using a load balancer to distribute the requests across these instances. This is known as horizontal scaling and is illustrated on the slide here. These two ingredients, namely stateless service replicas and a load balancer, are both absolutely necessary for horizontal scaling. Let's explain why. Service replicas are deployed on their own virtual hardware. Hence, if we have 2 replicas, we double our processing capacity. If we have 10 replicas, we have 10 times capacity. This enables our system to handle increased loads. The aim of horizontal scaling is to create a system processing capacity that is the sum of the total resources available. The servers need to be stateless so that any request can be sent to any service replica to handle. This decision is made by the load balancer, which can use various policies to distribute requests to service instances. If the load balancer can keep each service replica equally busy, then we are effectively using the processing capacity provided by our service replicas. Horizontal scaling also increases availability. If we have one service instance, if it fails, the service is unavailable. This is known as a single point of failure, a bad thing and one to avoid in any scalable system. In fact, in any system. Multiple replicas increase availability. If one replica fails, requests can be directed to any, they are stateless remember, other replica. The system will have reduced capacity until the failed server is replaced, but it will still be available, which is important. The ability to scale is crucial, but if a system is unavailable, then even the most scalable system ever built is still not very effective. Load balancing aims to effectively utilize the capacity of a collection of services to optimize the response time for each request. This is achieved by distributing requests across the available services as evenly as possible and avoiding overloading some services while underutilizing others. Clients send requests to the IP address of the load balancer, which redirects requests to target services and relays the results back to the client. This means clients never contact the services directly, which is also beneficial for security, as services can now live behind a security perimeter and not be exposed to the internet. Load balancers may act at the network level or the application level. These are often called Layer 4 and Layer 7 load balancers respectively. These names refer to the network transport layer At layer 4 in the Open Systems Interconnect, the OSI reference model, and the application layer at layer 7. The OSI model defines network functions in 7 abstract layers as shown on the slide here. Each layer defines standards for how data is packaged and transported. We'll explore the difference between these two load balancers on the next slide. Network load balancers distribute requests at the network connection level, operating on individual TCP or UDP packets. Routing decisions are made on the basis of IP addresses, and once a target service is chosen, the load balancer uses a technique called network address translation. This changes the destination IP address in the client request packet from that of the load balancer to that of the chosen target. When a response is received from the target, the load balancer changes the source address recorded in the packet header from the target's IP address to its own. Network load balancers are relatively simple as they operate on the individual packet level. This means they're extremely fast, as they provide few features beyond just choosing a target service and performing network address translation. In contrast, application-level load balancers reassemble the complete HTTP request and base their routing decisions on the values of HTTP headers and on actual contents of the message. For example, a load balancer can be configured to send all POST requests to a subset of the available services, or distribute requests based on a query string in the URI. Application load balancers are sophisticated reverse proxies. The richer capabilities they offer mean they are slightly slower than network load balancers, but the powerful features they offer can be utilized to more than make up for the additional overheads incurred. In general, a load balancer is going to have the features shown on the slide here. Basically, load distribution policies, health monitoring of individual service instances, elasticity, the ability to change the capacity of the system dynamically, and session affinity. And we're going to explain these concepts on the next slides. Load distribution policies dictate how the load balancer chooses a target service to process a request. Any load balancer worth its salt will offer several load distribution policies. HAProxy, for example, has 10. The most common ones are shown on the slide here. Round robin, the load balancer simply distributes requests to available services in a round robin fashion. Least connections means the load balancer distributes new requests to the service with the least open connections at any moment in time. HTTP header field means the load balancer directs requests based on the contents of specific HTTP header fields. For example, all requests with the header field client location is US Seattle could be routed to a specific set of services dedicated to processing traffic for Seattle. And finally, HTTP operation means the load balancer directs requests based on the HTTP verb in the request, such as post or get. Load balancers will also allow services to be allocated weights. For example, our nodes in our load balancing pool by default may have 4 virtual CPUs, and our load balancer allocates a weight of 1 to each of these. If a server with 8 virtual CPUs is added, we could assign it a weight of 2, so the load balancer will send twice as many requests its way. A load balancer will periodically send messages known as pings and attempt connections to test the health of each service in the load balancing pool. These tests are called health checks. If a server becomes unresponsive or fails connection attempts, it will be removed from the load balancing pool and no request will be sent to that host. If the connection to the service has experienced a transient failure, the load balancer will reincorporate the service once it becomes available and healthy. If, however, it's failed, then the service will be removed from the target load balancing pool. Spikes in request loads from clients can cause the service capacity available to a load balancer to become saturated, leading to longer response times and eventually request and connection failures. Elasticity is the capability of a load balancer to dynamically provision new service capacity to handle an increase in requests, a spike in requests. As load increases, the load balancer starts up new resources and directs requests to these, and as load decreases, the load balancer stops services that are no longer needed. An example of elastic load balancing is the AWS auto-scaling groups. An auto-scaling group is a collection of services available to a load balancer that is defined with a minimum and maximum size. The load balancer will ensure the group always has the minimum number of services available, and the group will never exceed the maximum number. The actual number available at any time will depend on the client request load the load balancer is handling for the services in the group. You can see this on the slide here, where we have a core group of services available for the load balancer and additional ones which it can connect to as needed. Typically, there are two ways to control the number of services in an elastic group. The first is based on a schedule, when the load increases and decreases are predictable. For example, you may have an online entertainment guide and publish the weekend events for a set of major cities at 6 p.m. on a Thursday evening. This generates a higher load until Sunday at noon. An auto-scaling group could easily be configured to provision new services at 6 p.m. Thursday and reduce the group size to a minimum at noon on Sunday. If increased load spikes are not predictable, elasticity can be controlled dynamically with a set of configuration parameters. The most commonly used parameter is average CPU utilization across the active services. For example, an auto-scaling group can be defined to maintain an average CPU utilization at 70% across the services in the load balancing pool. If this value is exceeded, the load balancer will start one or more new service instances until the 70% threshold is reached. Instances, of course, need time to start, to boot, often a minute or more depending on exactly what software they're booting up. And hence a warm-up period can be defined until a new instance is considered to be contributing to the group's capacity. When the group average CPU utilization drops below 70%, scale in or scale down will start, and instances will be stopped by the load balancer and removed from the pool because they're no longer needed. Elasticity is a key feature that allows services to scale dynamically as demand grows and shrinks. For highly scalable services, it's a mandatory capacity. Like all advanced capabilities, however, it brings new issues for us to consider in terms of downstream capacity and costs, and we'll get to these next week. Session affinity, also known as sticky sessions, are a load balancer feature that enables it to balance requests across stateful services. With sticky sessions, the load balancer sends all requests from the same client to the same service instance. This enables the service to maintain in-memory state about each specific client session, just as we described earlier with stateful services. There are various ways to implement sticky sessions. For example, HA Proxy provides a comprehensive set of capabilities to maintain a client on the same service, even in the face of node additions, removals, and failures. The AWS Elastic Load Balancing technology generates a HTTP cookie that identifies the service a client session is associated with. This cookie is returned to the client, and the client must send it in all follow-up requests to ensure session affinity is maintained. Sticky sessions can be problematic for highly scalable systems. They can lead to a load imbalance problem in which, over time, clients are not evenly distributed across services, and this is illustrated on the slide here, where two clients are connected to one service while another service remains idle. Load imbalance occurs because client sessions last for a varying amount of time. Even if sessions are evenly distributed initially when the system comes to life, some will terminate quickly while others will persist. In lightly loaded systems, this tends to not be an issue. However, in a system with tens of millions of sessions being created and destroyed constantly every minute, load imbalance is inevitable. This will lead to some services being underutilized while others are overwhelmed and may potentially fail due to memory exhaustion. Stateful services have other downsides. When a server inevitably fails, how do the clients connected to that server recover the state that was being managed? If a server becomes slow due to a high load, how do clients respond when they see massively increased latencies and start experiencing timeouts? In general, stateful servers create problems that in a large-scale system are difficult to design around and manage. Stateless services have none of these downsides. If one fails, the client gets an exception and retries, with their request routed to another live service. If a service is slow due to a transient network outage, the load balancer takes the service out of the service group until it passes health checks or it fails. All conversational state is either externalized in a cache or a database or provided by the clients in each request, so service failures can be handled easily by the load balancer. Stateless services enhance scalability, simplify failure scenarios, and ease the burden of service management. For scalable services, these advantages far outweigh the disadvantages, and hence their adoption in most major internet sites, a great example being Netflix. Services are the heart of scalable software systems. They define the contract defined as an API that specifies their capabilities to clients. Services are defined and executed in application server container environments that host the service code and route incoming API requests to the appropriate processing logic. Application servers are highly programming language dependent, but in general provide a multi-threaded programming model that allows services to process many requests simultaneously. If the threads in the container pool are all utilized, the application server queues up requests until threads and other connections to databases become available. As request loads grow on a service, we can scale it out horizontally using a load balancer to distribute requests across multiple service instances. This architecture also provides high availability, as the multiple service configuration means the application can tolerate failures of individual instances. The service instances are managed as a pool by the load balancer, which utilizes a load distribution policy to choose a target service for each request. Stateless services scale easily and simplify failure scenarios by allowing the load balancer to simply resend requests to responsive targets. Although most load balancers will support stateful services using a feature called sticky sessions, stateful services make load balancing and handling of failures more complex. Hence, they're not recommended for scalable systems.